Welcome to the series of video lectures on microwave engineering. Today in this session we will discuss the introduction of transferred electron devices. This article comes in unit 6 of microwave engineering subject. Before going to this transferred electron devices, let us discuss the semiconductor devices with positive resistances and negative resistance characteristics. See, the common characteristics of all active two-terminal solid-state devices is their negative resistance. So examples of active two-terminal solid-state devices are tunnel diode and gallium arsenide diode, etc. Let us see this tunnel diode in short. So these are the VA characteristics of tunnel diode. When VA characteristic tunnel diode, if you increase the voltage till the peak voltage, the current through the device increases. If you increase the voltage, the current also in the tunnel diode increases. If the voltage, input voltage is above the peak voltage, the current in the device starts decreasing till the value voltage. Once the input voltage is above value voltage, the current in the device again starts increasing. The region, you can see this, in the region between peak voltage and value voltage, if you increase the voltage, the current through the device decreases. So this region between peak voltage and value voltage is called as negative resistance region. This is the peculiar property of tunnel diode. So due to this, tunnel diode is used as oscillator in microwave frequencies. See, the real part of the impedance, that means these active devices, is negative over a range of frequencies. Let us discuss the positive resistance semiconductor devices first. In positive resistance semiconductor devices, the voltage and current through the device are in phase. Let us discuss what is this positive resistance semiconductor device. Suppose this is a positive resistance semiconductor device. So this is the voltage applied across the device and this is the current flowing through the device. If you increase the voltage, the current in the device also increases. So that means the voltage and current are in phase. That means if you increase the voltage across the device, the current through the device also increases. Example, PN junction diode, etc. Now, in the voltage drop across positive resistance semiconductor devices is positive and the power of I square R is dissipated in the device. So see, the voltage drop across this device is positive, and the power of I square R is dissipated in this. A power is dissipated in this device. Let us come to the negative resistance semiconductor devices. Let us see that in negative resistance semiconductor device, the voltage and current are out of phase by 180 degrees, especially in negative resistance region. So the voltage drop across the negative resistance is negative and a power of minus I square R will be generated by the device in this region. See, suppose this is a negative resistance semiconductor device, for example tunnel diode. If you increase the voltage across the diode, the current through the device decreases in the negative resistance region. So due to this the voltage drop across the device in this region is negative and a power of minus I square R is generated by this device in this region. So in other words, the positive resistance absorbs power, so that is passive devices. The passive devices absorbs power, whereas negative resistance generates power, active devices. This is a very, very important point. So that is the positive resistance. If the semiconductor device consisting of positive resistance, it absorbs power, the device absorbs power. If the semiconductor device consisting of negative resistance region, it generates power instead of absorbing the power. So these are some of the characteristics of positive resistance semiconductor device. So what happens with the positive resistance semiconductor device? They will absorb power, whereas negative resistance semiconductor device will generate power in negative resistance region. So this is a small introduction about this semiconductor devices. Now let us discuss the microwave transistors and transferred electron devices. Let us see the differences between these microwave transistors and transferred electron devices before going to the definition of transferred electron devices. See, in microwave transistor, the transistors are operated with junctions or gates. So the transistors generally consisting of junctions or gates. BJT consisting of two junctions, JFET consisting of junctions, where these transistors are operated with the help of junctions and gates. Examples: BJT, JFETs, etc. Whereas transferred electron devices are bulk devices having no junctions or gates. See, in the transferred electron devices, there are no junctions or gates. Examples: gallium arsenide, etc. Gallium arsenide, indium phosphide, etc. So these devices, gallium arsenide devices, do not consisting of any junctions. Now, the majority of transistors are fabricated from elemental semiconductor materials such as silicon or germanium. As you know that most of the semiconductor devices, transistors, are fabricated from either silicon or germanium. Coming to this, the transferred electron devices are fabricated from compound semiconductor materials such as gallium arsenide, indium phosphide, cadmium telluride, etc. So these are fabricated from compound semiconductor materials, that is, by mixing third group elements and fifth group elements, we can make this compound semiconductor materials which are transferred electron devices. Now, say, coming to this microwave transistor, they are operated with warm electrons whose energy is not much greater than the thermal energy, which is 0.026 electron volts at room temperature. So they are operated with warm electrons. These transistors are operated with warm electrons whose energy is not much greater than thermal energy. For coming to this TEDs operate with hot electrons whose energy is much greater than thermal energy. So this is very, very important point. The transferred electron devices operate with hot electrons. The energy of these electrons is much greater than the thermal energy. So these are some of the differences between microwave transistors and transferred electron devices. So microwave transistors are generally fabricated from silicon or germanium, whereas these are fabricated from compound semiconductor devices by mixing the third group elements and fifth group elements. Now, coming to the transferred electron devices definition, let us see the transferred electron device, why this is called as transferred electron devices. So for this, first let us see this diagram. This is energy band structure of n-type gallium arsenide. So this is the energy band structure of n-type gallium arsenide. As you know that any semiconductor device consisting of valency band, forbidden band and conduction band. So this n-type gallium arsenide has a peculiar property that in conduction band you can see two valleys. So this is called as high mobility lower valley. These terms are very, very important. High mobility lower valley and low mobility upper valley. So there are two energy bands again in the conduction band. This is lower valley, this is upper valley. This upper valley is about 0.36 electron volts from the forbidden band. Let us see what happens with these two energy bands. Now, when the applied voltage across the gallium arsenide exceeds a critical value, so that is 2000 to 4000 volts per centimeters, when the voltage applied across the gallium arsenide exceeds this value 2000 to 4000 volts per centimeters, there will be a transfer of electrons from high mobility lower valley to low mobility upper valley. See, once the electric field exceeds a critical value or threshold value, so then there will be a transfer of electrons from this lower valley to upper valley. You can see this. The electrons will transfer from lower valley to upper valley because the electrons are transferring from lower valley to upper valley above some critical value. So this is called as transferred electrons. What is transferred electrons? The electrons are transferred from lower valley to upper valley above some critical electric field. So that's why these devices are called as transferred electron devices. Due to this transfer of electrons from lower valley to upper valley, this shows negative resistance characteristics. This device shows negative resistance characteristics because of transfer of electrons from lower valley to upper valley above some critical value of electric field. So these devices are named as transferred electron devices. So this is about this article. So very, very important topics are there in this. negative resistance devices and positive resistance devices is discussed first. Next, the differences between microwave transistors and transferred electron devices is discussed. Next, the transferred electron devices definition is also discussed in this session. Thank you.